Hey, hi, welcome to episode number 4. So we were discussing in our last that what does mean by designing an inverter? Is it merely just getting your PMOS and NMOS and connecting them, or we have something else? And this could be a very important question because it's directly related to your designing of CMOS inverter. And as you know, inverter is the nuclei of your digital electronics. So if you can design your CMOS inverter perfectly precisely for each condition, and probably you can easily design or you can extend this result for any other digital CMOS circuits. So that's why interviewer tend to ask this question most commonly. So we have our well-known CMOS inverter. Question is that what does designing mean? See, one thing you need to be really sure about is that this CMOS design or anything, as a designer, we don't have flexibility to tweak every variables. For example, if you see your current equation of your MOSFET, and again current equation has many variable, and as an engineer you might want to know each and every equations or variable why they are coming. But as of now, as of today, we are learning CMOS inverter, so don't go or don't push yourself to derive the current equation. For now, just believe that current equation is true and it is what it is. Don't try to derive it now, it will be a time wasting phenomena. So if you don't remember your current equation, then this is your current equation. If your MOSFET is in the linear region, because we have two current equation roughly, actually not two, we have three. There are some other equations which we will discuss in our further episodes, but this is roughly your current equation for your MOSFET, right? And here you can see we have many terms. We have some voltages, and then we have some Kn. We don't know what this Kn is, but if you remember, your Kn is actually the process variable. And the most important thing is that you can't touch your Kn dash. Why? What's the difference between Kn and Kn dash? Your Kn is your W by L, and then this term, your mu n c epsilon ox, and then tox. And as a designer, we don't have any control over this because this is a foundry decided value. Foundry means if it is your TSMC will tell you this value, what they have. You can't touch this thing. After that, you have the liberty to play with this fellow. And this is your W by L. And in my last episode, I just given you one hint, and that is if you see your MOSFET in the 3D domain. In the 3D domain, and this is your drain, and this is your source, and this is your gate. This could be your L, and this way if we extend, then this is your W, right? So we have only freedom to change our W by L. And as a digital engineer or a digital design engineer, probably L is also fixed, because what we tend to do, we tend to use the smallest possible L which we have. As an analog engineer, we might modify our L depending upon situation, but as a digital design engineer, most probably L is fixed. Now the question is that if we have our W by L for PMOS, is it equal to W by L of NMOS? Is this the simple equation? Probably not. If it's so much simple, then I wouldn't have discussing it here. And probably you know from somewhere, sometime you have read or somebody told you that yeah, your W by L of P should be 3.5 time of W by L. Or probably you might say no, it is 2 time of W by L. So here we gonna explain, or we gonna decode this thing. Is it 3.5? Is it 2 or what? So if this thing is interested for you, then please don't forget to like this video. And for new people, I am Rajdeep and I am currently working as CAD engineer with Intel. So let's get started. So now let's write our current equation for NMOS and PMOS separately. And I hope you can do it easily, but for you, let me write it quickly. So for here, I'll be just subscripting one N to differentiate it from our P. And yes, I understand it's a little long equation and you don't need to remember it, but it's a good idea to remember it. So we have this thing, and why I'm writing this thing, because I wanna explain you what's the size of W by L of P and NMOS. So see, if we have our NMOS here, sorry, our inverter here, probably I have written 100 times inverter till this date. This would be your V out and this would be your V in. Perfect. And one thing you need to know is that here we have our ID. It is the drain current. Here we have the source and here we have the source, right? So we have ID. So the first thing you should be clean and clear, and that is a concept from your KCL, Kirchhoff current law, is that if we have a point, if current is going inside to that point, then we have some, if it is a positive, then current going out of that point would be negative. So that means the current inside your PMOS, ID current inside your PMOS should be of negative sign of your current inside your NMOS, because this ID is going inside to your PMOS and from here it is leaving your PMOS, right? So it is leaving your PMOS but it is going inside to NMOS. So it could be like this or it could be like this also, no issue, just replace them, both are okay. So let's take only one for now. So this is the first equation. After that, what we gonna do, we gonna see the VTC of our inverter. So if this is your V in and if this is your V out, you can see this is your V in and this is your V out, then how the voltage transfer character should look like, and as an ideal it should look like this. So if your VDD or the maximum possible voltage is 2.5 volt, then inside also we can give up to 2.5 volt V in. So we need to have this transition at the halfway, and that is 1.25 volt. This is the ideal VTC characteristic we need. When our V in is 0, our V out should be the highest possible, that is 2.5, and when our V in is of highest possible, then our V out should be V out from here. From here if we see V out is 0. So that is the ideal characteristics. But you can see when it is moving from this part to this part, it is having a time when your V in and V out are of same. At this point your V in is equal to V out, right? And when we are designing our inverter, we need this transition point should be in between. From VDD and the 0, it should be in between. And why in between? For a larger noise margin. Noise margin I haven't dealt yet, but in my last lectures I have roughly explained you what does noise margin mean. So to have a larger noise margin, we want this transition point should be at of mid, right? And who is deciding our mid? That is when we have V in equal to V out. So probably in this equation, in these two equations, we do some trick to get that thing, like when V in equal to V out, what is your W by L for PMOS and NMOS? That's our aim here. So before going to those aim, let us quickly write down all the things. For example, we have VGS of N. So we need the value, and if you saw this inverter here, then you can see your VGSN is nothing but voltage at gate of NMOS minus voltage at source of NMOS, and voltage at gate of NMOS. At the gate of NMOS, what's the voltage? It is your V in, and at the source of NMOS, it is your ground, or it is 0. So that means our VGSN is V in directly. Likewise, if we want to know our VGS of PMOS, then again at the gate we have V in, but at the source we have VDD, so minus VDD. And likewise, if I want to know the VDS of N, so it is again at the drain. So at the drain I have V out for our NMOS. For NMOS it is V out, so it will be V out. And at the source, VDSN, VD, voltage at drain minus voltage at source of the NMOS. It is again ground, so it is 0, so it would be V out. And if I wanna write for PMOS, then at the drain we have our V out, and at the source we have VDD. And what we want a point where our V in equal to V out. That point would be the transitioning point, and that transitioning point should be at the halfway, and that would be a perfect design for our CMOS inverter, right? So that means this thing I could write if I take this extra equation, and that is V in equal to V out equal to Vm. So that means here for every equation I can directly replace V in or V out with my Vm. So that means this will become your Vm minus VDD. This thing will become your Vm minus VDD. This thing will replace to Vm, and this thing will replace to Vm. So it becomes so simpler. Now I will put these voltages to this equation number 1 and the equation number 2. And after putting them, I have my equation number 3 also, that IDP equal to minus of IDM. So IDP plus IDN should be equal to 0 according to KCL, right? But before putting them into the equation, let me do some more simplification, and that is, let us assume that our VDD is 2.5 here. You can assume anything. So that means our Vm would be 1.25. Why 1.25? Because we want our V in equal to V out should be at the halfway margin of VDD to 0. And what's the halfway margin from VDD to 0? It is your 1.25 voltage. So that means I can again simplify this thing, and I can directly write here VGS is nothing but your 1.25 volt. Your VDSN is again 1.25 volt. Here I can easily write it is your 1.25 minus VDD, so it is 2.5 volt. And you can see from here it will be a negative. And for your PMOS, VGSN is always negative. If you don't relate to it, just ignore for now. And here again I can easily write it is 1.25 minus 2.5 volt. So if I just write it down, so it will be something negative 1.25, or let me directly reduce the cluttering here, and it will be directly minus 1.25 and minus 1.25. Now I'll put this thing into my equation, and I'll get the answer for what should be my WYL with respect WYL of P with respect to WYL of my NMOS. And that is what we want, that we want to design our inverter, and which should, it won't be ideally looking like this, it will be looking like this. Actually it will look like this, but this midpoint should be at the halfway. That's our goal, that's we want to. So let me do it for you, but I'll strongly recommend you just pause your video now and try on yourself, okay? Then only you get the insight. So I'll be writing our IDP plus IDN should be equal to 0. My IDP is KNP WYL P, and then now here is the interesting thing, and that is our VGSP we already have derive, and that is our minus 1.25, and minus VTP I don't know now, so I'll take one example. Like we need the some practical example of threshold voltage of your NMOS and PMOS. So VTP I'll tell you what is that. Then this is there, and VDSP we have this, so it is again minus 1.25 and minus 1.25 whole square by 2, and that is, and this thing plus the current of NMOS, so that is KN WYL of NMOS, and then your VGSN is already derived, and that is 1.25 again. VTN I don't know here. VDSN is 1.25 minus 1.25 whole square by 2, and that, and this should equate to 0, right? So here we have how many variable we have this KN and KNP. So these things are process defined. So For sure, TSMC, UMC or Intel, they have given us this value whenever we are designing our inverter. So we can get this thing from their PDK or the detail they have sent to us. So I'll just tell you those things. VTN and VTP are also process dependent in some extent. So those value also will be find out from their documentation. From the foundry documentation. So here I have one documentation, and this is not a foundry documentation, but I have taken this from one of the best book for digital electronics guys in this book. This book. So I have taken from this their reference, one of the example, and the reference is there here. So we have a 0.25 micron meter CMOS process, and there this is your VT here. And these are other things which we will ignore for now. We will be ignoring this thing, and this is your Kn for NMOS and PMOS, and this thing will be ignoring for now. So we have these two value, we'll be putting it to our equation and we'll get our result. And if you put this thing here, before putting this that let us just rearrange this thing. So to rearrange this thing, let me do this thing, and that is your WYL P over WYL N equal to this thing. See, this whole thing from here it will go to your right side, so it will get a minus sign here, Kn under cap, and it is of NMOS. WYL from here is already went here. Rearranging, I'm just rearranging. If you're confusing, you do it yourself, you'll get this thing. And then we have this thing. So VTN we already have from the from that data, and what was that, and that is, if I'm not wrong, then it is for NMOS 0.43 and for PMOS it is minus 0.4. Before calculating, let me write it directly here. We can have our calculator and we can easily calculate this thing. So this thing don't have much of value here, so let me write it here quickly. And then in below this thing, this whole part will come below, so it will be KNP, and then minus 1.25 minus VTP, and your VTP is minus 0.4, so it will be plus 0.4, and then again minus 1.25, and then minus 1.25. so whole square will just eliminate this minus part, so it will be 1.25 square by 2, and you need to solve it from here. And if you solve it, you need to just be a little bit sincere. And for Kn and Kp, again let me show you what's the value. For Kn, the value would be this is your Kn value 115, and this is your Kp value. So you just need to put them here, and if you put them sincerely, then the value you will be getting, and that will be closer to 3.5 or something. It will be closer to 3.5. And what is closer to 3.5? It is your WYLP. Let me write it little. WYLPYWYLN, or which imply your WYLP should be roughly equal to 3.5 times of WYL of N. It will be roughly 3.5 or probably 3.8 also. There is no golden number of 3.5. It depends on your process parameter, on your voltage. If it is VD 2.5, then you will get some answer. If it is 5, then you will get other answer. So this is a rough sense. So never say that it is 3.5. Okay. And in general, in practical scenario also, we never use this equation actually. We never keep our WYL or the size of PMOS 3.5 times bigger than the NMOS. This is the ideal thing we should keep. Like for example, here we got a result of 3.88. So we should have taken 3.88, but we don't take. Why? Because one thing is that if we keep so much bigger PMOS than NMOS, then there is a size penalty. We need to have more size for an inverter. So ideally what we do this thing, equal to 2 times of WYLN. And you will tell me that hey, you did so much of hard work here in this page in this page, and after getting a correct result for this mid transition point, you are saying no, let roughly put it 2 here. So what's the point? The point is that if you see this graph, and actually I'll be highly encouraging you, recommending you, if you are not in your final year, then please try to simulate this curve. And this curve is actually W by N. For different W by N, for different W by P over W by N, because our L is constant, right? So if I say W by L of N, P, and W by L of N, then L will get cancelled because roughly they are equal. In digital design they would be equal. So that means W by P by W by N. So this axis is your W by P by W by N, and this axis is your VM. VM is your that where we have V in equal to V out. So this is the point. So what they did, they changed this W by P and W by N. So for example, first time they have simulated this inverter for W of P of 10 and W by N of 5. So we have the 2 time ratio. They have simulated it and they have just tried to get out that number when our V in equal to V out, or the number of VM. What is that? Then probably they have make it 3 times. Then probably they made it 4 times, and likewise they have plotted this graph. And from this graph, one thing is very crucial to understand, and that is whenever your W by Pn, whenever your W by P by W by N is, and from this graph you can you need to know that this is for your VDD of 2.5. So what we want actually this transition point should be at the half. So half means 1.25, roughly around this we want, right? And they have found that your W by P over W by N of 2 and W by P and W by N of 3.5 or whatever number you got are resulting near about same VM or the transition point, because it is not so sensitive. It is a log paper. If you draw it in your linear paper, you will find probably a flat line here, probably a flat line, right? So that's why they went with 2, number 2, like ratio 2, because it will be a good alternative between the penalty of size and the transition point. Now a very important question, and the important question is that do we always design our PMOS double size the NMOS for a CMOS inverter? This could be a question in your interview. So let me answer this thing very intuitively before going to more detail, and that is, let me get a free space here. So for example, this is your inverter. I hope you are familiar with this thing. This is the symbol of your inverter, and I am giving a input here, right? And your input is like this. It is below and then it is going up and then it is down, right? And this is your maximum possible voltage or the high voltage VDD, and probably this is your VM, the halfway margin when your output should transit. So from this we can directly write here, it is very easy, that anytime my input is lower than VM, I'll be getting higher, and anytime it is crossing this point, then I'll be also crossing my output and I'll go here and so on. So this is your for output. But now let add some twist here, and the twist is that, and just be sure and just remember that we have designed this inverter for VM to be halfway of your VDD by 2. This is your halfway. We have designed like that. But now we got one signal, and that signal is little bit of wild, and that is, it is okay when it is at the high, but whenever it go low, it is like this, it is bouncing and then it is settling down. Now tell me, if you design your inverter like this, then what will happen? Then it will be a disastrous output actually. If I just roughly draw these points whenever it is crossing your VM, then up to here it will be down, then whenever it is going below VM it will go up, then down and up and down, which is not the intention of this circuit, this inverter, because we know this is actually the portion of when our signal is at low, but due to some problem with our signal or some noise of our signal, it is fluctuating there. So if you get some input like this, that time it is always good to have your VM slightly above the mid range. And now there will be again a question how to push your VM up or down, because if we keep our PMOS twice the size of NMOS, then it is roughly at the halfway. Now we want to push our VM above, up. So now what to do? Should we make our PMOS bigger or should we make our NMOS bigger? And what would be the reverse if we want to push our VM down? And in real life scenario, there are many occasions when we need to do these things. So now this is a question for you. We already know that our PMOS is of twice the size of NMOS. Now further we want to push our VM up. So that time what will happen? Will we increase our PMOS more, the size, or we will decrease the size of PMOS more? So this is a very interesting question, and this type of insights are required in all the VLSI interview. So I hope you enjoyed this episode. If you subscribe to this channel, and this answer I'll give you in our episode number 5. Till then, see you, tata, bye bye.